Greetings and welcome, friends. Today we're going to talk about some new trigonometric identities, specifically the sum and difference identities for both cosine, sine, and tangent, respectively. Let's start off with a little example here for us. And we already derived these formulas a moment ago, or at least for cosine and sine. Let's take a look at this. Yeah. All right. So here's an example. Find the exact value of cosine of 735. And I'll throw a little degree symbol in there for funsies. Right now. Bam. Degrees. 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 Bam. So if I want to find the exact value of cosine of 735, that means I can't just plug that into a calculator because that would give me a decimal approximation. It would not be exact. So I subtracted a couple of 360s from that, probably 720 degrees total, and I got cosine of 15 degrees. Okay, so that's coterminal. I didn't have to do any reference angle work. And now 15 degrees, I don't know, I don't have like, I've got a 0-degree finger and a 30-degree finger for my hand trick, but I don't have like a finger growing in between them that I know of. So I don't have like a 15-degree finger, right? But I can rewrite cosine as the difference 45 and 30. Interesting. Interesting. And I do know the values of cosine at 45 and 30. Now, how's that going to help me? Well, I'm going to use this trigonometric identity. All right? Which you've got on your little sheet that I've equipped you with as well. So this is the cosine sum and difference identity. Notice this identity has a plus or minus here. Main thing I want to point out about this identity is it's plus or minus here, but then it's minus plus there.
What is that weird looking?
So this says that the cosine of alpha plus beta, all right, if I have two angles, would equal cosine alpha times cosine beta minus, if I'm adding here, then I'm subtracting here, all right, sine alpha sine beta. In our case, I've got cosine minus, all right, 45 minus 30. So cosine of 45 minus 30, I'm going to use the minus version of this formula, all right, which is a plus in the middle of it, okay? So notice the flip-flop on those signs there. So cosine 45 minus 30 is going to be the same. Well, let's see, let's label this. My alpha is the 45 degrees, and my beta is the 30 degrees. So let's just fill this in. So cosine 45 minus 30 will be, according to this formula, cos 45 times let's see, beta, so that's 30 degrees, minus sine alpha sine beta, so sine 45 times sine of 30 degrees. So what we've got is the following. Cosine 45, hand trick, that's root 2 over 2. Multiplied by cosine 30, that's root 3 over 2. Minus sine 45, root 2 over 2. Sine 30 is a half. Root 2 times root 3 is root 6. 2 times 2 is 4. Minus root 2 times 1 is root 2. 2 times 2 is 4. And now I could just combine these. They already have a common denominator. That's the square root of 6 minus the square root of 2 all over 4. So this is the exact value of cosine of 45 minus 30 degrees, or cosine of 15 degrees, or cosine of 735 degrees. Exact value, no decimal approximation. I agree, it's not necessarily very pretty, but we are able to calculate it exactly. Since I was able to happen to break this down into some angles that I already knew. Not too shabby. Not too shabby. So let's take a look at another example here. This one I like here. Oh no, let's see. Let me throw some. There it is. I got to get a clear shot of it from my plan book here. This is about Heinrich Hertz. I don't know where he was from. I think. Oh no, he was a German physicist apparently. Exemple. You don't have to write down all these facts, but maybe just the very end of it would be helpful to us. It says in 1887, Heinrich Hertz. All I can think of is Heinz ketchup right now. Like I'm just like combining the first 4 letters and the last letter of his last name. A German physicist, all right, discovered electromagnetic waves. The period of a wave is the shortest interval of repetition. All right, you guys might recall that back in sinusoidal functions from Math 4. It says, show that sine of pi over 6 plus 2 pi is equal to sine of pi over 6. So in this case, the period is 2 pi. So to prove this, we could actually use one of our new identities, the sum and difference identity for sine. Sine. Here we are. And you've also got this equipped on your little sheet. It's available to you. Now, thing I want to point out, sine of alpha plus beta. Notice this time the plus signs match and the minus signs match. So that's significant. Although in this case it's not sine, sine, and cos, cos. They're flip-flopped a little bit compared to the previous identity. So what I'm claiming is that sine of pi over 6 plus 2 pi, all right, that I should be able to use the plus version of this formula here, right? So that's going to equal, well, alpha will be the pi over 6, beta will be the 2 pi. So we'll have sine of pi over 6 times cosine of 2 pi, all right? Plus, because the signs match, plus and plus, for the sine function anyway here, cosine alpha times sine beta. Sometimes I actually even switch these around if I feel like sine, cos, but no matter. So this will be cosine of pi over 6 times sine of 2 pi. So now notice I'm just trying to verify that this is equal to sine of pi over 6. So I'm hoping that somehow this will be the answer and the rest of this will simplify out. Let's see. So question, what is cosine of 2 pi? Cosine of 2 pi. Think about unit circle. 2 pi is the same right here. All right, this point's location is 1, 0. Cosine is the same as the x-coordinate. That is 1. Aha! That's the same as multiplying by 1. Equals cosine of pi over 6. That's technically we could do some math with that if we wanted. That's just what's root 3 over 2, I believe. That's pi over 6 is 30 degrees. But sine of 2 pi. Question. Sine of 2 pi would be the y-coordinate, because it's sine and not cosine, which is 0. So notice what I'm left with, this whole thing 0. Adding 0 to this is the same, and I in fact do get sine of pi over 6. Right? Which, like I said, we could calculate that. That's the same as sine of 30 degrees or a half. So this is verified, in fact. So good news for our friend Heinrich Hertz. Yep. All right. Oh, I love this problem. Did you just say who killed Heinrich Hertz?
Who killed? Really excited for this problem.
Oh, yeah, I am excited about this problem. This problem's all sorts of goodness right here. This one you might want to write down.
A short example of examples.
That's good. That's good. Let's see. Maybe I'll even make this a little bigger, just because this problem, it deserves it. This problem's huge in China amongst all my viewer. I had to say that singularly, I guess. The plurality would have been a lie. Let's see. Find the value of sine of x minus y if angle x is between, oh, that's supposed to be a 0, sorry.
That's a 0.
Yeah, that's not, those aren't supposed to be theters. My bad. So x is between 0 and pi over 2, and y is between 0 and pi over 2. What quadrant is that describing? That's quadrant 1, right? You guys agree? Quadrant 1, right? That's the same as saying between 0 and 90 degrees. Let's see, here we got, and then they gave us a couple facts. They said sine x is equal to 9 over 41, and sine y is equal to 7/25. Yeah, cynics. So, let's see, I'll recopy my little formula in here just to have as a comparison. Why not? Why not, shall we? You, of course, would just be looking at your sheet or something to that effect. So this is the formula I'm looking at. Right, so let's write out sine of x minus y, according to this formula, should equal sine x cos y. Let's see, this is a minus sign, so what do I want?
No, minus.
In this case, it's a minus.
How do you know which formula to use? Whether it's the first example or...
Well, this one said sine, so that's why I'm picking sine.
Okay.
And then a plus b, or alpha plus beta, sorry, so that's why I'm using the plus sign. So if it matches the top, it matches the top. If it matches the bottom, it matches the bottom, sort of thing, for those signs there. So I want minus in this case, so then this would be cos x times sine y. Now notice, I already know what values. I know sine x and I know sine y. What do I need to know in order to finish calculating this? I need to get real cozy with this problem here and figure out what these other values are. So maybe, I don't know. I just spotted it, I rolled with it. So how could I find cos y with my given information, the information I already know? Now check this out. I know sine y, I want cos y. I can find that information here, right? Okay? So I'm just going to plug in what I know, solve for what I don't. All right, so let's find, part 1, let's find cozy. All right, how am I going to do that? I'm going to plug into this trigonometric identity. This is a classic Pythag right here. So I've got 7/25 all squared plus cos squared y is equal to 1. So squaring that, that's 49, 25 squared, guys. What's that? Is that, it's not 625, is it? 625, it is, plus cos squared y equals 1. To solve, I'd subtract this guy from both sides, right? So I'll get cos squared y equals, 1 is the same as 625 625ths. I think you'd agree. Right. So 625 minus 49 is 576. You don't say. And how do I find cozy? Root both sides. Now question, when I root, I technically get a plus or minus here. However, let's see, square root of 576, that sounds really familiar. That's 24. Yeah, this is 24/25. Oh, sorry, 570. I did write a 9 there. Guys, that was a 6. My apologies. Wait a minute. It's 6. It's 6. Yep, good call. Thank you, friend. So, cozy. Do I want the positive or the negative version of this?
Positive using quadrant 1.
Oh, all the way back to the top. That's the main reason they gave us those facts, was that we need to know quadrant 1, and in this case, I now know that this is the positive value, right? So, similarly, I now have to find what other values. So I just found cozy. Cos x. How am I going to do that? Exactly the same way. Exactly the same way. All right. Do you think I could fit it over here? I'm going to try.
Don't worry,
I'm going to try my best. So let's see, to find cos x, what do you think I'll do? I'll use the same exact Pythag identity. And I'm going to relate it to sinks. So that's going to be 9/41 squared plus cos squared x equals 1. Square both sides. That's going to be 81, 41 squared. I'm not familiar with that one. 16/81. Oh, I see what they're doing here. That's a good choice. Giving us some friendly numbers here. Subtract that from both sides. I end up getting cos squared x equals 1600 Pennsylvania Boulevard over 1681. What do you think I do? Root both sides, technically plus or minus, but what quadrant am I in, Sam? First quadrant, so cosine is going to be positive. Square root of 1600, I believe, is 40 41st. So now what do? I'm just going to plug all of these guys into their respective locations in this formula. Let's see, so cos x is going here, cosi is going there, all right, sine is going here, and sinks is going here. So let's see. Let's see if I can plug all these in and figure out what this is equal to. So 9/41 multiplied by, what was it, cosi? Yeah, 24/25, and it was minus, and then let's see, 40/41 multiplied by 7/25. At least these are going to have a common denominator. Equals, let's see, 9/24 is 216 over 41 times 25, 10/25. Interesting, interesting. Minus, what's that, 280? Interesting, 10/25. This is going to be negative. 216 minus 280. It's negative 64 10/25. Now, does this make sense for the minus part? Now think about what we knew. We knew we were in quadrant 1 for both angle x. Say this is angle x, and let's say this is angle, this whole angle is angle y. All right. If I do angle x minus y, and both of these angles are less than 90 degrees, what quadrant am I landing in? Yeah, I would have the difference. It would be this amount, but it would be down here, right? This would be angle x minus y. So quadrant 4, right? Sine is positive here and here, and negative here and here. I would expect this to be negative. So it does, in fact, make sense. It does work out. Okay? All right, so that's a little bit weird. But to show the big context of this problem, all I did was I wrote down the equation, and then I just was like, oh, I'm just going to plug in everything I know. And oh, I had a couple missing parts. I just had to go find those. Right? Classic sort of problem right there. Good problem. Let's look at one more. One more. And here we've got evaluate the following. Tangent of 285 degrees. And you might be like, wait a minute, Mr. Waddy. We don't know the sum and difference identity for tangent yet. But, oh, you do. Take a look on your little sheet. I happen to give it to you. This is what it looks like. Now, technically, you might have not even needed this, because using the quotient identity, I would expect that tan of a plus b would just be the sine of a plus b over the cos of a plus b. And that would have worked. But this is like a simplified version of it so that it made it its own identity. Tan of 285. All right, if I want to calculate this exactly, I need to make it somehow a combination of angles that I already know. All right, angles that, or that I can calculate exactly. It turns out that 285 is the same as 240 plus 45. All right, when I'm thinking of angles I know, I'm thinking about, right, 30, 45, 60, 90, stuff like that, right? Are angles that I do know. Now, 45 I clearly know, but what about 240? What am I going to do with that? Yeah, if I find the reference angle, is that an angle that I'd be familiar with? Actually, what quadrant is 240 in? Yeah, that's quadrant 3, and that is 60 degrees from the x-axis. So this is the same as 60 degrees-ish. But is tangent positive in that quadrant?
Yes.
Yeah, and it's positive in that quadrant. So that's great news for us. So,
Positive equal to 60 degrees? The reference angle.
yeah, the reference angle for 240. Yeah. So this actually would end up being the same as 60 plus 45. I could actually plug 240 in here and then throw the reference angle in afterwards, and that's fine. And in those cases, I'd actually still, if tangent was negative in those quadrants, I'd change those signs respectively. So let's set this up. So this is going to be tan of 60. Now let's see. Question, am I doing plus or minus here? Plus, oh, it looks like my formula. I forget the little minus sign there. How sad. Let me throw that little... There, now you can't tell. Can't tell. Tan of 60 plus tan of 45. That is the ugliest tan. It's like spray-on tan right there. All over 1, and is this plus or minus? Minus, because the minus is on top. I love it. Minus tan of 60 times tan of 45. Okay. All right. So let's calculate this. Tan of 60 degrees. Does anyone know that one off the top of their hand? I believe that's the square root of 3. Tangent of 45 degrees is 1 over 1 minus the square root of 3 times 1. So this is square root of 3 plus 1 over 1 minus the square root of 3. Wait a minute, I can't leave a radical in the denominator, friends. I know you have not seen this for a long time, but in order to get rid of a radical that's part of like a binomial, I have to multiply by the conjugate. Does anyone remember that at all? Oh wow, that's classic math 3 skills right there. In the numerator, I could FOIL this out. Actually, that's a plus b all squared in the numerator. You guys can actually start packing up. I'm going to keep going with this video, though. We're just about done. So this pattern is a squared plus 2ab plus b squared. And this one is the denominator is a plus b times a minus b, which is equal to a squared minus b squared. And let's see, so up top I would have 3 plus 2 square roots of 3 plus 1. And down bottom it's a squared minus b squared, so that's just going to be 1 minus 3. So that's 4 plus 2 square roots of 3 if I combine my like terms. Yeah, you guys are good to go if you'd like. All divided by negative 2. So that's actually negative 2 minus the square root of 3. Crazy sauce. Crazy sauce. So, because I divided the negative 2 into both of those top terms there. 4 divided by negative 2 is negative 2. Yeah. So anyways, thanks for watching, Internet friends. Have a great day. Bye-bye.